Yes.
Education mission project.
I've been to Venice.
I have born in Buenos Aires, I lived there for many years, but now I'm living in the south. Wow, the south. Now I'm here. And what are you doing? Masters? Engineering or science?
And you?
Masters. And then we're thinking of going back to Brazil.
No, probably not. I don't know. I'm about to get an internship.
Sometimes I go to Brazil football show.
Before I stayed.
Only one. I've been here almost 4 months. Only one guy. Hey, Brazil. Now Argentina. He was from Brazil. So now we got the World Cup.
Yeah.
Fun. Nothing but match.
I enjoy Argentina.
So we have Messi. Suarez. I don't know. We haven't won anything. Last time we won something on 1993 or South America.
Really?
That's the last thing. After that, we won nothing. The last one was 1996.
What was it? 1996? What happened in 1996? 86.
86. That's the last one.
Yeah.
When was the last Brazil World Cup? 2002? Korea. Japan, Korea. So that was last one.
Yeah.
2006 was for Germany.
Yeah. We lost to France. And then last World Cup we lost to the Netherlands.
And in 2006, Italy won. 2010, South Africa.
Okay. So nice. I've got another student job, so nice to meet you. But you had to leave to Korean South Films. How are you signed to? That's good. Yeah, this is yeah, I want you to look your thing, and also since you
Y'all ready, Thomas?
We got a couple more minutes. No, sorry, we're right on time. Everybody ready? I dig that shirt. Is that like Barney's baby?
No.
Barney's a purple dinosaur, or Barney, sorry. Bobby used to watch Barney, didn't you?
It came out long after I was past that age, Tom.
So you know how you're supposed to talk and introduce somebody? This is one of my oldest and dearest friends. We started, I think the first time I met you was in the computer room on the 3rd floor, and you had been there a couple of days working. And Bobby had a different entrance into the industry. Bobby was a frac engineer, and he was getting his petroleum engineering degree at the same time, if I recall. And if I also recall, he might have taken a break from school and come back. And he then enrolled, and we were in graduate school together through the mid-'80s. He, I don't know how to say this politely, but I think he was one of the first people in petroleum engineering to take a Master of Engineering degree. I don't know why Dr. Jennings talked you into that, because you worked harder than the rest of us. But at that point, Master of Engineering, we didn't really know what to do with it. But Bobby rewrote the Texas Railroad Commission well testing manual. And I've got a copy of it somewhere on the web. Actually, I made a version of it. And it was a step change. It was a beautiful piece of work. And one day, the phone rang, and I got a call from Mike Fekovich. And he said, I'm going to murder you guys for coming up with a new Texas gas well testing manual. I said, you're talking to the wrong guy. You want to talk to Dr. Jennings. My name's not on this thing. He goes, yeah, well, I know you know who it is. And I said, well, what's your opposition? And he says, chief engineer or whatever he was for Phillips Petroleum, he said, we have to follow whatever the state guidelines are. And if the state adopts this, then we have to do all this new high-powered work and everything else. And he says, but everybody else is going to cheat. Because if you've ever read the old manual and you read the new manual, the old manual is like a piece of paper that you write on and make some notes. The new manual is you must do this analysis, you must do that analysis. And so I said, I don't understand your point. He said, if this is implemented, we have to do the new analysis. And we're not afraid of doing the new analysis, but everybody else is going to do the old analysis. You guys have no idea what I'm talking about. But the new analysis is more conservative. So what does that mean? That means that whenever you finish your form and you write your number in the little box, and somebody over in the state office says, oh, his number is 24, your number is 48. So your allocation is going to be twice as much as his. But it's two wells next to each other that are producing the same way. You did it the old method, he did it the new method. That was going to be what in Fekovich's mind was going to happen. Do you remember that? Yeah. And then Bobby stayed on and did his PhD, did a phenomenal piece of work there as well. He went to work for Schlumberger, and we reconnected in the early 90s. And Bobby had written a solution for the Cinco and Main fracture case, and I needed it. And he was nice enough to loan it to me. He had programmed it in Fortran. And I
gave it
confess,
to Jay, too, Jay Rushing.
Yeah, he helped us both. And you know how you have the computer rooms here? I would go in at night, and I would turn jobs on, and I would lock the doors so nobody could get in, and let it run all night. And that was how we would generate solutions back then. And Bobby and I wrote a couple of papers together. He's been working on the same problem for 25 years. 25 years. How old are you? Yeah. So he's been working on this problem longer than you've been alive. Is that kind of weird? No? You like that? He's been working on something longer than you've been alive. So what he's been doing lately is he's been working on performance analysis, analogous to what I do. He does a little bit differently. He works for Schlumberger, of course. He's a senior advisor, and he's the author of several software packages within Schlumberger, some of which you'll never hear of because they're proprietary. He's author of at least, half a dozen patents, I would suppose, maybe more. He won't talk about those either. He patented his latest, or is in the process of patenting his latest solution for hydraulic fracturing, which is a direct solution. It takes 27 pages of notes, but it's a direct calculation of the hydraulic fracture solution. For those of you who don't realize, that is a tremendous accomplishment, but of course it's just another day in Bobby's life to do things like that. Bobby wrote a book with Steve Poston, who had been a faculty member here. He's also written a lot of reports and papers and that sort of thing. In a way, you know, I always blamed our generation, Bobby, for not having an opportunity. We were born in a trough. And Mr. Rod and I were talking about how you know, things were tough when we got out of school. And I don't think these guys understand what tough was. You know, like nobody got a job. That's why I went to graduate school. You know, there wasn't. If you remember, one of our classmates really never got a job, and I can't mention his name, but then he went to get a PhD because he never got a job, and then he worked in the same job for 25 years, and they eliminated it, and he was like, what do I do now? And I said, well, you messed up. You should have gotten some different skills. But you know, so there's a message to you. Make sure you don't take the first job that comes your way. Make sure you continue to learn and adapt. I guess the easiest thing to do is let him go on. But Bobby is an example of what the unexpected could do. We were both very average students. I wouldn't venture to compare my skill set to Bobby's, but he's truly an extraordinary engineer. He's made Schlumberger more money than you can possibly imagine.
He didn't give me much of it.
He didn't give you, he gave you a watch. He's got some awards. He's got a watch. I'll go ahead and tell you because he won't, but Bobby is a real estate magnate. He decided that he was going to create some value for him and his family, and you now own what, 90 houses, 80 houses?
71.
Okay, sorry, my count's wrong. He was buying a house a month in Houston. They're all essentially paid for, right?
They're free and clear.
He has 100% occupancy, and he runs a company that runs his houses. He buys them. And
My wife does that.
Sorry, well, you're the brain behind it all.
She does most of it.
She does the billing and the brute force on people who are late with the rent, that sort of thing. But what I'm trying to tell you is sometimes people fool you. You know, you look at it and think, okay, work for Schlumberger for what is it, 26 years now?
No, I've been doing 20, almost 23.
You know, and you say, well, that guy's, it's a long time, you know, they'll give him a nice retirement, that sort of thing. No, he didn't see it that way. And his name pops up in places where you don't expect. You've got a truly unique experience today. So he's going to be here till 8. Hopefully we don't stay that long so we can get you back on the road to go home. But Bobby, the class is yours. Most of these guys are familiar with reservoir engineering to some degree. There's a couple of geologists and a couple of people who are more production side, perhaps, but I think you can appeal to that as well. I think you would refer to yourself as a resduction engineer or something like that. Bobby's a bit above the production and a reservoir engineer. So I hope that was an ample and adequate introduction. Bobby's one of my favorite people. He's been under-recognized by the Society of Petroleum Engineers. Work on that in the years to come. He's also a tremendous contributor in the service sector, a professional service sector. He's done everything I've ever asked him. We've been on some mighty strange committee assignments. been in the back of a taxi in some really strange cities, but with no further ado, you've got a real giant here in front of you. Take advantage of the opportunity to talk to him, listen to what he's got to say. He's only got 26 slides, and he's here as long as you need him. So, Bob, welcome.
Good evening. Tom had asked me to talk about shale gas forecasting, how good are decline curves. This is essentially a talk that I gave in Brisbane in November. We had a PRM, Production Resource Management System. It's SPE's efforts at trying to quantify reserves and stuff. We had a workshop on it in Brisbane. And this is a presentation, basically the presentation that I gave there. So one thing, the question was, how good are decline curves in estimating forecasting the shale gas future production? They can be very good or they can be very, very bad. Depends on how they're applied. Basically, you have to understand what you can actually extract from a production decline curve analysis and judiciously use those to forecast in the future. Some parameters, as you'll see at different points in time in the production history, such as early time, you'll see many of the early parameters such as permeability, fracture half length, fracture conductivity. Some parameters you may not see for quite a period of time, such as drainage area, if you see boundaries. So it depends on what you actually see in the production performance as to what you can extract from that data and what you can use to forecast in the future with it. There are various different types of decline curve models. There's generally two general types that are involved. These include empirical models such as Petkovich's model, ARPS's late time stems, or there are even more theoretical models such as the work that Tom and all of his students and co-workers have developed over a period of years. There's various other models we can add to it as well. So there are generally two different basic categories of production decline models we use for DCA, decline curve analysis. I'll talk about the applications and limitations of these models. Primarily what we're going to look at for unconventional reservoirs, or for shale gas in particular, is many times all we see is transient production. We don't really see any late time behavior in the wells at all. If all you have is all you have is transient data, you don't really know where to, there's a uniqueness problem. You don't know really where to put the data on the graph. All the early transient stems are essentially uniform or parallel. They're symmetric. You really have a uniqueness issue as to where to peg it, unless you have a little bit of data on the transient side and a little bit of data on the boundary dominated side. That's true in general, but we can still estimate where we think we would see boundary effects. That's some extrapolation techniques I'll talk about in just a little bit. But the big issue is accuracy of the match, as well as uniqueness of the match that you get. And there are specific limitations that are applicable to unconventional reservoirs, such as the issue of capillary effects, capillary pressures. Extremely high capillary pressures, not just normal. I mean, we're talking tens of thousands of PSI in a gas water system. So if you have examples there where you've got like a set of mercury injection capillary pressure data, you can calculate relative permeabilities from it. You can also convert that to a gas water system or a gas oil or any type of fluid system you want, as long as you have the appropriate properties. And many times we typically ignore the capillary effects, even though they're huge in our production analyses. And I'll show you some stuff that we can do with that as well. And I'll give you a few examples, field examples. There's some synthetic examples as well as some field examples, and provide some concluding remarks. One thing to note, and this is true of any kind of numerical inversion that you do on any kind of historical data. You cannot invert for a parameter, in this case the production data record, in which the effect of that parameter has not been exhibited in the record. So if you have a parameter such as drainage area, and all you have is transient data, the effect of that parameter has never been exhibited in the production performance. You cannot invert for that parameter directly. You can estimate, there's various techniques for extrapolating or estimating what that parameter is, but you cannot directly invert for it. So if you take that production data and you hook it up to a model, a decline curve analysis model, with a nonlinear regression engine, such as Levenberg-Marquardt or any other kind of regression model, it'll give you any kind of wild answer you want. There's no uniqueness to it whatsoever. but you can do some judicious extrapolation techniques. Cartesian extrapolation techniques, you can estimate what those properties are. But there are specialized techniques for that. There's also a bias that when you look at the empirical models, you're trying to fit it to an empirical model. You're trying to fit it to some kind of general shape that you're looking for. Those parameters may have essentially no fundamental basis in the reservoir properties. So when you do an empirical analysis, decline curve analysis, you get a B value and you get a decline exponent value, or a D value. You have to be able to try to relate those to some fundamental properties such as permeability, fracture half-length, drainage area, skin effect, any of these other parameters. There's not really there are ways to estimate it, but it's not really a direct one-to-one correlation between some of those parameters. There are techniques you can use to try to estimate some of those. The empirical technique is commonly used in all of the banks, and if you do, many of the operators use them for decline curve extrapolation of cash flows, production, future production, as well as cash flows. They're very simple. There's, I don't know, hundreds of different types of production analysis software companies out there that generate code based on the empirical models, Petrovich type models, that you can use to extrapolate in the future without having any other information other than just production data, forecasting it in the future, fitting it and forecasting it in the future. Theoretical models, you're doing actually an inversion. You're trying to extrapolate some of the reservoir properties. You have a basic model, a theoretical model that you're trying to fit to that data and extract formation properties, estimates of the formation properties from it. And it has at least a partial theoretical basis in fundamental reservoir engineering. Basically, you've got a transient solution, and you're trying to couple it to like an exponential late time behavior, which is part of the fundamental solution. As I'll say, it corresponds to the classic exponential decline in late time. It's more fundamentally sound, but it requires a greater engineering skill and understanding of what you're doing. All right. Talk about the applications and limitations. The applications, any reservoir that produces fluids under natural flow, or if you have measured bottom hole pressures, that you don't have to calculate them from the surface. If you have PWF values from like an ESP or something, you can do a production decline curve analysis. The limitations are that generally the quality or the quantity of the data may be a limiting factor. I mean, we're talking about, at best, we're hopefully getting daily data. Sometimes the best you can get is monthly data. The coarseness of the time increment that you're using really hinders you sometimes as to what you can actually extract from the production performance. But ideally, the best data that you can get is just as small of a time increment as possible. Daily data are hopefully better. Hourly data is better. The uniqueness that you have for inverse solutions or match results, this is particularly true for all you have is transient data. There's multiple realizations that you can get for those types of data sets. But there are techniques that you can use to improve that, and I'll show you some of those here in just a minute, based on some work we've done earlier. Talk about the accuracy as well. And there's also some graphical analyses we can use for improving the match parameter selection. The rate transient analysis dimensionless variables are given here. This is the definition of dimensionless wellbore flow rate in oil field units for liquid flow, corresponding gas, dimensionless wellbore flow rate for gas reservoirs, and then conventional oil field units. The dimensionless time and the dimensionless cumulative production for liquid and gas in oil field units. Right? That's the rate transient analysis variables. Here is the decline curve analysis variables and how they're related to the rate transient. This is the dimensionless decline curve variable, time value. Like if you look at the Petrovich decline curve, this is the kind of parameter he's plotting, where he's coupled the transient stems and the late time ARP stems. He's got a dimensionless time parameter on the abscissa. On the ordered axis, he's using the dimensionless rate, dimensionless decline rate, and how it would be related to the exponential decline. This B value of 0. Dimensionless cumulative production, this is an integration of that variable, as well as an integral function that Tom and some of his coworkers have developed, integral function and a derivative of that integral function. These help you in determining some of the early transient matches. because it gives you three curves to match on simultaneously instead of just one. It helps remove some of the uniqueness issues that early transient parameters. One thing I like to work with too is a dimensionless pseudo production time, like a dimensionless Horner time or dimensionless material balance time. You can see here, essentially it's dimensionless cumulative decline production by the dimensionless decline rate. That's has issued here, or here it is in terms of the material balance time function and the drainage area, dimensionless drainage area. So they're all interrelated. It depends on how you set it up as to what you can extract, what groups of parameters you can extract from the decline curve analysis match. This is just an example showing what you can get from an empirical decline. This is a classic way that banks or any other reserves estimates are commonly done. We have an empirical match. This is like fitting it to effective itch decline curve analysis. You fit the data here, and you can extrapolate it in the future. This is actually the hyperbolic match here. It actually turns into exponential a little off the graph here. This is on a Cartesian scale, so it's hard to see it. But this is just a classic type of decline curve analysis that we run into. Where if they're trying to estimate reserves, book reserves through the company, or if they have to take that estimate to the bank, try to borrow money on future building projects, this is the kind of reserves estimates you typically get. All right. Oh. There we go. We can also do a more theoretical based decline analysis match. This is like one of Tom's plotting functions. Here we have dimensionless rate and also the integral derivative function versus dimensionless decline time. Right?
You just change the side, do your finger.
Did I touch it? Yeah. Let me go back one. Does it automatically advance? You just touch it?
Yeah, it's live. You can do just about anything with your finger, so be careful.
What I have here is you can take the same rate decline data and plot it like this, or you can plot it in terms of dimensionless cumulative production, which is the next slide. Here I have an example data set. It's like a little bit less than 30 days, about 30 days of production. This is an unfractured vertical well. Yes, this is an unfractured vertical well. This is a Bakken well that will actually flow prior to production, or prior to fracturing. And here I have that's 82 days. But it would actually flow before we actually fracked it, right? We can match that thing on basically any set of these early transient stems, any pair of them. They're all symmetric. That's the uniqueness issue we run into many times. We don't really have any data on the late time part of the curve. The same data plotted on a rate versus cum production decline curve. Again, you can match it on anywhere up and down that transient set of stems. But you can also plot it like this. This is a paper that I gave in Florence, Italy, a couple of 3 years ago, where you plot it against cumulative production. You're plotting the rate decline, like the Petrovich decline rate, but you're also plotting against this sort of production time, dimensionless material balance time. Simultaneously, there's only one place on that graph that data will simultaneously fit. If you look here, what this match is, this QVD match, like 0.0, 0.03, 0.0, something like that. If you go back to the previous graph, go back the other way. Same spot. Not this one, the QPD graph. This one. Same point on QPD down here. So you know where to peg it now. You know which pair it has, which ones it has to fit on, right? Which one of these pairs does it actually have to fit on? Because it jump back to, that's it. Yeah, 101.
Can I ask you a question?
Yeah.
Have you found wells that don't fit?
You have to pick the correct well model, of course. You'll have data that won't perfectly fit on every curve, I'm sure. But in general, in fact, I'll show you some data sets where you can get in some cases where they'll perfectly fit. But generally, you can make them fit on any set of decline curves. It may not fit as well as you'd like, but All right. Anyway, this is at point 1, right? Right here. That's where it came to. So you know where to peg it. This is the only place that will fill that graph. There's simultaneously converging functions, right? Only one place it'll fit. Once you have this match, go back to the previous graphs, you got it pegged. I've got a little Excel spreadsheet I'll show you. You can simultaneously move it and match it and come up with this kind of an analysis. So we didn't have any late time data, but we could extrapolate to what it would be. Right here, this is all transient. This is the onset of boundary dominating flow right here, way off out here. So if this is about 82 days, this is almost 1,000. Way off out here, where the end of my glasses are. It takes a while to get there. All right. We can also look at the same data plotted up. This time we're plotting it against material balance time function, dimensionless material balance time, or dimensionless pseudo production time function. It's the same data. And I also threw on like a well testing type derivative right here. So you can do all kinds of combination of matches. In fact, there's even some more exotic stuff that I'll show you we've looked at. Right? That was for an unfractured well. Now let's look at finite conductivity fractures. Here we have, this is a horizontal, I'll give you the same geometry for a horizontal well drain hole as well as a vertical fracture, single fracture. Right? Excuse me. These are different dimensions drainage area values. This is the fracture in the middle, and this is essentially a square. Is AD of 4 or an XE to YE ratio of 1. So its aspect is a square, or every rectangle in between. Right? Rectangular drainage area. And this is for a closed system. So we'd model in a tight, low permeability formation. Basically, what you're draining is the length of the horizontal lateral or the fracture. You get very little, if any, production from beyond that length. In the conventional reservoir, you will get some. But in an unconventional reservoir or tight reservoir, very little production comes from beyond the length of the linear source. We model it. We can verify that fact as well. We also look at, for a range of dimensionless conductivity values. Here's a very high conductivity fracture, basically infinite conductivity. You get a set of family of curves. You get, as a function of dimensionless drainage area and dimensionless fracture conductivity, you can get a whole family of curves that you can match this thing to. They have unique shapes as well. This is for high conductivity fracture. Look what it looks like for low conductivity fracture. Completely different. Here you have bilinear flow, long bilinear flow. This is quarter slope right here. And this is the corresponding, this is that pseudo production time match. Here's the rate match right here. On the previous graph, you have quite a bit of linear flow. This is linear, not quarter slope. This is a half slope. Well, the way it works out. All right. This is quarter slope here. You look at the basically start at one of the like around about here. It's about here about 4 of them. You'd come up as a quarter. Right. This is an example as in that paper, in that Florence paper. 30 days of production. This is a fractured well. In fact, I modeled this one like what you'd see in a Wilcox well in South Texas. Typical well that you'd see down there. The input values that I used for the simulation was 10 to the minus 3 millidarcies, fracture half length of 950 feet, and of course the fracture conductivity was 50 millidarcy feet. When I did the manual matching, the graphical analysis, type curve matching, these are the results that I come back with. Not numerical inversion, but manual type curve matching. This is 30 days of production right out to here. Gives you 0.2. Dimensionless chem production value about 0.2. You'd have to go out, this is 30 days, it'd be almost a year before you'd see any limits. Any reservoir limits. It's purely transient data. So this is one way to extrapolate to onset of boundary effects, or what you'd estimate drainage area. Here the drainage area is right at 16 acres when we model it. But we can invert that without ever actually seeing it. We can estimate what it is. We can't directly invert it, but we can estimate it. It's just one technique. You do the same thing for horizontal drain holes. Here the parameter we're using is dimensionless wellbore length, LD, which is like the half of the wellbore length, total wellbore length divided by the net pay thickness. LD is LH over 2 divided by H. Also, you have dimensionless drainage area and aspect ratio as well. Here you have a family of curves. Here I'm looking at, this is GCA solution. Here we're looking at a different set of values. We're here at a high or large value of dimensionless wellbore length. And here we're looking at for low, this is 50, the other one was 500. So you can see the difference in the shapes of the curves. Here I've also plotted on data on this curve as well. This is right at 31 or 2 days of production data. Almost right about here, right? So we're about a year away from seeing boundaries. And these are the input values. 100-acre drainage area. This is the correct aspect ratio, and 0.05 is your permeability. Just manual decline curve matching with purely transient data. All right. Here's some exotic curves. You can throw together all kinds of plotting functions that you want to. We can actually generate unique derivative functions. So this is an unfractured vertical well, right? For different values of RED stems, like a effective H rate decline, or Tom's harmonic lake time stem, negative unit slope. If you plot it as like a well testing derivative like this, you can get unique derivative functions that correspond to that same set of data you can match against. There's many different ways you can do it. And very few people ever tried this, but I'll show you a spreadsheet program that works with this kind of analysis. We can also look at multiple fracs, horizontal wells intersecting multiple transverse fractures. This is commonly what all of our completions are in North America now. In fact, we do this on a daily basis. We have interpretation models that we use on a regular basis where we can look at quantitative diagnostics. We look at linear flow, compound linear flow. These are the different flow regimes we'll point out here. You can also look at multi-rate or multi-IBC forecasts. So you can have a changing bottom hole pressure forecast in it. You can couple it to nodal. In fact, I think it's on one of the slides coming up in a minute. Excuse me. You can look at desorption of the shale. Of course, for gas reservoirs, you have to use pseudotime and pseudopressure. Pseudopressure for sure. Pseudotime if you can look at boundary-dominated data. As long as it's pretty transient, you can get by with just pseudopressures. It is a very fast semi-analytic solution. This comes out of Michael T's or Michael Tamlin-Eigen's big old thick diffusion book. If any of you have ever seen it, it's every solution for the 2 and 3D diffusivity equations there are. Every kind of boundary condition you can imagine. It's like 2,000 pages of nothing but solutions. The diffusion equation. That's what this code, this Advanta is the name of this code. That's where it came from. We also do multi-well deconvolution. You can actually look at the effect of each lateral in a multilateral system or multiple fractures. Each individual one. If you have individual flow rate contributions, you can do a fracture stage or individual fracture analysis, but you have to have that individual rate history to go with it in order to do that kind of analysis. But it has that capability. We also generate a drainage map like this. You can actually simulate what the pull pressure distribution or saturation distribution is at a given point in time. And we can look at the different flow regimes, and you have a flexible production schedule. We can look at multiple laterals. In fact, this is the well in Saudi. We have 3 multi-fractured laterals. This is one of the Menara projects. We can run it simulation for different time levels. You can see here what the different forecasts of each of the different laterals are. This is very, very fast. It's a gridless solution. We're all analytic, or semi-analytic.
This is Michael's?
Michael's book, yeah.
It looks that good.
Oh, yeah. Like I say, they're not vessel functions, they're theta functions.
Yeah.
All these solutions are theta functions. This is an Advanta. It's very, very fast. This takes about 3 or 4 seconds.
We have this product, or we should have it here.
Probably do.
If you guys want it.
Yeah. This is in Atlanta right now.
At Fanta, like Atlanta, only at Fanta. I didn't realize it was at.
Oh yeah, it's fast. It's like 2 or 3 seconds. All right. This is an example in Eagle Ford in South Texas. This is a real field example. This is a horizontal well with multiple transverse fractures. This is the kind of production history you see. Your gas rate comes on initially about 10 million a day, and after, this is 500 days of data, it's down to about 900 MCF per day. You see the water production is drying up. There's very little any condensate, and it's just negligible. This is basically a gas well. But this is basically the flowback to the fracture. First 100 or so, 150 days, this is frac water. Because after about 150 days, you're down to about 12, 13 barrels a day. It's not much. All right. This is another type of diagnostic we can do. This is just plotting up the raw production data. Nothing else, nothing fancy. We have the pressures. We also have the rate. Well, the pressures are computed from the surface. We have surface flowing surface flowing pressures and flow rates. We calculate bottom hole pressures and we convert it to pseudo pressures. So here we have the plot of the cumulative production function, which is pseudo pressure drop normalized cumulative production. You get long linear section data. Well, the flow rate does the same thing. It's linear section. This is compound linear. It lasts for years, sometimes. In fact, this is 500 days of data. It's still a good one. It hasn't ended the compound linear yet. It can last quite a while. But you can do these types of analyses as well. There are analytic solutions for this, asymptotic analytic solutions for this type of behavior. We can analyze. I think we do it in the diagnostic plots. All right. So this is a real field case. This is the kind of data that you see. Again, you see some noise initially, but once it lines out, it becomes very, very linear. All right. We can also use Martin and Perrin's linearization. That same data. This is the same data set. Based on the production rates and the fluid properties as a function of pressure, you can estimate what the relative or effective permeability ratios are of each of the produced fluids. Reference to the principal fluid, which in this case is gas. So the oil or condensate to gas or the water to gas, you see how those effective permeability ratios change. Of course, you know what the conditions for Martin and Perrin's linearization are, right? Negligible capillary effects, no changes in saturations with respect to time, or very, very small saturation gradients. Negligible, basically. So basically it's static. The saturation is not changing. But with those kind of assumptions and no gravitational effects, neglect those, then you can estimate what the effective permeability ratios are, just from the historical production data. Now, what is the effect of increasing the SRV, the stimulated reservoir volume of a multiple fractured horizontal well? Here we have 2 cases. We look at a 4,000-foot lateral or an 8,000-foot lateral with twice the number of fractures. 120 fractures in the longest case and only 60 fractures in the shortest case. They're evenly the same distance between them. So basically you're doubling the SRV. You can also see that it increases the recovery as well. And this is in a finite system. I forget what the drainage areas were, but basically it's the same volume, same reservoir volume to start with. It's reference to this length, and this other one is just half. It's completed in the middle of it. So basically, with using twice the number of fractures, you're accelerating the production. You're getting the same amount at the end. It gives you the accelerated production. What happens if it's in an infinite system? It outruns it all the way through, right? So you can see this kind of behavior as well. This is the purely transient behavior. You're transitioning here. Of course, you have your compound linear in this region. Here's your linear, compound linear. Transition. You get a very, very long late time, or middle time, I should say, middle times. This is a laterally infinite system. You have no boundaries. So you can model all this. In fact, this is with Erdol's solution. OSCAN solution for his trial linear model. No, correct. This is the Eclipse. This is the Eclipse. We compared it with Erdal's solution as well.
One question from the previous slide.
Mm-hmm.
You get the same recovery?
This is it.
It's just an acceleration production?
No, I'm wrong. This is actually time. This is not Cume production. This is time. It's still outrunning it. These are two different systems. The finite system is twice as big. I told you wrong. It's twice as big. It's outrunning all the way through. If it was the same size system, yes, they would. If this was Cume production, it would converge to the same point. There's no percept recovery calculation hooked up to it. It's just analytic solutions. But here we're only looking at production from the SRV. We have no production from the region beyond the SRV. The next slide, here we've already gotten past the SRV region. This is the end of the SRV region right here. Here we're pulling fluid from beyond the SRV region. Outside of where the length of the fractures are and the length of the lateral that has the fractures in it. Actually, you're pulling fluid from far field in the reservoir.
You don't have the EUR of these wells?
No, I don't. This is synthetic data. I can go back and figure out what it is. I look at the simulation runs, but I don't know what the number is. But it's a synthetic example. We were looking at the question was, what was the effect of increasing SRV, putting more fractures in it, making a longer fractured well. And so theoretically, yes, it increases the production. So, I didn't want to put a whole lot of slides there. Didn't want to take up all y'all's time. But fundamentally, as I said earlier, if you've got a parameter that you're trying to invert, you cannot directly invert it, but you can estimate what it is many times using specialized diagnostics. But directly, you cannot invert that parameter if it's not exhibited in the production performance using a typical or classic inverse analyses. The production behavior can be used to evaluate reasonably reliable or accurate estimates of reservoir and fracture property or well properties, depletion effectiveness using rate transient, decline curve analyses, and specialized diagnostics. You really need to use every kind of analysis you've got, not focus on just one type of production analysis. You got DCA, you got RTA, you got any kind of numerical model matching, diagnostics, everything. And you'll get probably the most reliable and best answer you can get with it. The graphical analyses of only the transient performance of the data. It's difficult if all you have is empirical decline curves, but you can, if you have a reasonably accurate models such as like we use with Fedkovich or either couple of models, the harmonic decline, the hyperbolic decline with a late time stem on the exponential. You can use those to estimate future recovery, but you got to do it judiciously. You can't just blindly do it. And you need to couple with all your other analyses as well. There's a couple of articles there. This is from SPE, Recommended Evaluation Practices for Decline Curve Analyses. This is a book here that Steve posted, that Tom had referenced, that Steve posted, and I helped him with there a little bit writing it. And these are really the only two publications we have in SPE for decline curve analyses currently. Did I go through it too fast? Any questions?
Questions?
Those boundary parameters as drainage area or ability that you get from the transient only data, have you ever had the chance of checking them after the years when you get data from the boundary side and you can check and if
Go back this way just a second.
if that well ever gets to the boundary side data.
I thought I had the other one there just a
For
second.
example, here you estimated at 16.4 acres drainage area with transient data. If you wait several years,
Well,
have you ever checked that?
this one, I know what the answer is because I used it to forecast it. The production is forecast, it's synthetic. So we know it works because this is forecasted. The input values were 950, right? Frac length. aquarium is 10 to the minus 3 millidarcies. And it's right at 16 acres.
But those data
Are
will
transient
come
only.
from transient data.
Those are only transient data.
Yeah.
But we can estimate what the drainage area is with only transient data. This is a synthetic example, so I know what the answer is. With field data, you don't know. I mean, unless you run it clear on into late time, you would never know until you actually see late time behavior. But here we know what the answer is to start with. We know this is the input values, or right at the input values. Now we have the transient data, we can extrapolate it. See, there's only one place in this whole graph set where the data will fit.
Yeah. I was asking if you had the chance of having from the same well after some years boundary data where you can invert those parameters.
It'll give you the match. In fact, let me show you something here. Let me get out of this, escape. Here we go. Oh, I don't have my machine here. No, I've got the spreadsheet on my program, on my computer. I don't think it's on the stick, the memory stick.
You do this matching in Excel spreadsheet?
No, just I built a prototype, a demonstration prototype for this Excel. This is all Excel right here. But I have a program there that you can move it on one. All these graphs are tied together. You move it, and it'll simultaneously update all of them. All these different types of analyses I've shown you. Like right here. Like these types of graphs, it has all these built into it. It has all these different types of matching functions hooked up simultaneously. You move it on one graph, it'll automatically update all of them. And so you match it simultaneously. This is the one I use to do most of the matching. Right here. That gives you the anchor point, the QPD value. And once you have it, like almost 0.02, 0.15 or something like that. Once you have that, you know where to put it on here, right? You know where that match point is. Then you know which pair to pick up. That removes the uniqueness problem. All you have is transient data. Okay. Because on this graph, the cume graph, as well as the, it also is a time graph. You can basically match on any pair of symmetric, and all you have is if all you have is transient data. With this other graph, there's only one spot it'll fit.
I want to give these guys a little context. Why are we doing production analysis rather than pressure transient analysis?
Well, because typically, there's one real good reason is rate transient analysis is basically you have a constant or terminal pressure solution, right? Somewhere in that system you got a terminal pressure, whether it's constant bottom hole pressure, constant wellhead pressure, separator back pressure. Somewhere in that system there's a terminal pressure that's governing that inner boundary condition, that solution, that outflow. If nothing else, it's stock tank. The atmospheric pressure at the stock tank. Somewhere in that system you've got a terminal pressure. Excuse me. So ideally, we have rate data as a function of time, so we can do our rate transient analyses. Decline curve analyses fall in that same category. Well testing, where you can actually shut the rate into zero, is ideal for using pressure transient solutions. Because then that's one of the solutions. You can actually shut it down to a rate of zero. With the rate transient solutions, you can't really shut them down to zero. You can bring the pressure up close to whatever the average reservoir pressure is at that time, and it'll go approximately to zero. But with well testing, you could actually set it to zero. Shut in a rate of zero.
But I was thinking more, we waited our whole career for production analysis to come to the forefront.
Yeah.
Everything that was sexy and cool was pressure transient analysis. Why don't we do pressure transient analysis in shales?
Well, you'd have to wait forever.
That's
Build-up tests would take forever on these
exactly
things.
the right answer.
Well, like here, all you see is in 30 days, you know what a 30-day build-up test would cost on a high-pressure well in South Texas? You're talking a big chunk of change, every one of them.
Are they willing to shut the wells in?
Not a
No,
chance.
because in a shale, you can devastate the formation.
It won't come
They're
back
gonna
as
shut
strong.
in. They might let you have an opportunity shut in, or they're going to shut the field in. But a 30-day shut-in in a shale well could be a
Lost
kiss of
production.
death.
And it may be permanent loss production too.
Shales tend to reseal whenever their pressure builds back up.
Well,
And also, what do you get from, I mean, you've explained to them that you're looking for characteristic signatures so you can see inflection points and so forth. You gonna get that from pressure transfer analysis? No way.
well,
Not unless it's a,
it's going to be difficult with, well, there's several reasons, but besides the terminal pressure inner boundary condition, with rate transient analyses, you're always working with rates, and you're integrating rates to get cumes. That tends to smooth out the noisy production data. If you're working with pressure transient solutions, you're taking pressure data or pressure drawdown data, and you're calculating derivatives of it. You have to have at least one or two functions to work with. So you're calculating derivatives of an already noisy flow rate normalized pressure drop or just pressure drop function, and you're magnifying the noise. This is just noisy as can be. So the rate transient solutions have the advantage of being a lot smoother functions to work with too. But fundamentally, theoretically, they have ideally the same basis.
that's the same solution.
You can
same
calculate one from the
reservoir.
other in Laplace space and then invert it back into real space. They're theoretically the same solution. You can calculate either rate transient or pressure transient solution from the same analytic expression in Laplace space.
Pressure in a terminal solution implies constant pressure.
Somewhere in that system, you've got a terminal pressure governing the production of that well. So whether it's a constant bottom hole pressure, constant wellhead pressure, constant separator
Somewhere
back
must be
pressure,
constant.
somewhere in that system, you've got a terminal pressure governing the production of that well. That's terminal pressure solution. These are rate transient solutions, where you have a terminal pressure and you're calculating corresponding rate. Pressure transient solutions are where you have a terminal rate and you're calculating the corresponding pressure response.
So by terminal you mean constant?
No, it just means, well, it does mean constant at some point, but it means that's the inner boundary condition.
In boundary.
That's the terminal. It's the inner boundary condition, whether it's terminal rate or terminal pressure. There's some inner boundary condition value that's governing the production of that well.
He's not talking about superimposing it, Santiago. He's talking about, like in Petty 620, when you had a solution you had to drive for either constant rate or constant pressure.
When you get to
This is a constant pressure.
right, all the type curves that we generate here, these are like constant bottom hole pressure type curves, right? Rate transient type curves. But when you get to these models, all you have to do is apply superposition, and you can generate, use that same solution to generate this kind of response. Here you have the rate and the pressure. This is the inner boundary condition we're using to drive it as a decreasing bottom hole pressure and function like that. If you do the nodal analysis, where you have terminal wellhead pressure, you're just doing the intersection between the inflow and outflow curves in the nodal system analysis. It's using the same type of constant bottom hole pressure solutions to do it.
So what's next, Bob? What's missing in the literature that we need? As you and I come to the end of our careers, what's our bucket list of things we'd like to see happen?
There's a lot of things to be worked on. One of the big ones, of course, is being able to calculate, like I'd like to be able to calculate inflow along a long lateral. You have a horizontal well with multiple fractures or even unfractured, it doesn't matter. You have some fractured, some unfractured. You'd like to know what parts of that wellbore are contributing to production. You have to be able to compute it some way. You have to have the rate distribution somewhere along that system to go with the pressures that you have at the wellbore. Some inference for the inflow rates. That's what we'd like to know, what the contribution inflow along that wellbore is. Also multi-phase. But really, I mean, we're using approximate solution techniques for this, but we really ignore a lot of the true multi-phase flow issues. We don't take into account any of the delta permeability changes with time. I mean, you saw these changes. I mean, here they were Oh, I'm sorry, wrong way. How much change in, one more slide. How much change have we had in all the permeabilities? About 4.5, less than 0.5 on the water. Condensate didn't change much. This is basically a dry gas well. You get that much kind of change in water production. So when you're calculating a multi-phase pseudo-pressure function coupled with these analytic models, we're not accounting for this. That's the subject of some work that I've got a paper coming into the Amsterdam meeting that'll be covering some of this. In order to do that, you've got to actually start out with independent measurements of relative permeabilities. There are capillary pressures that you can use to calculate relative permeabilities from. So I have some work that I was doing in the Bakken. I have mercury injection data, capillary pressure data. You can use Berdeen's model to calculate the corresponding relative permeabilities, plug those into a multi-phase pseudo-pressure integral transformation. You can calculate a multi-phase pseudo-pressure function that you can use to analyze this type of data properly without ignoring all these multi-phase effects. It has both capillary pressures in it as well as relative permeability effects. And it effectively linearizes the diffusive side of the diffusivity equation. Not the storage side, the diffusive side.
So when 30 years ago, you were rewriting a well testing manual for the state of Texas. I'm sorry it didn't get accepted, but what do you
Mike didn't
recommend
want it to.
these guys to think about?
Well, it would have brought us up to speed a lot closer. The only thing close to it, I mean, there was really far in advance of it was the Canadian well testing. The Alberta Energy Resources Conservation Board well testing, gas well testing.
What I'm saying is an inspiration point. You know, your professor said we need this. Mm-hmm. If you said to these guys, we need this, what would it be?
It'd have to be something to do with better understanding of what we've actually created. I mean, we can't even tell you for sure what we've got.
Characterizing the formation from
and the well
pressure data that makes sense.
Yep.
And we're lost right now because our measurements are far away from where these things are happening. That's my personal view.
Yeah.
I don't know that we're ever, I mean, even if we had distributed pressure, I mean, I know we have distributed temperature, but these things are expensive. You know, what's it going to tell us? And another surprise these guys don't realize is all these wells are interconnected. They frack into each other. And you can change one well and 3 patterns away, the other one will change.
I'll give you a little clue as to what I'm working on right now. I'm working on the stuff in the Middle East, in Saudi Arabia. They've got permanent installations, permanent monitoring, the Menara stations where they have, in these laterals, they have multiple laterals. And they have Menara stations which include Venturi flow meters. They've got water cut meters. And they've got pressures, both upstream and downstream pressures and temperatures. So what we're trying to do is be able to calculate, and we're doing deconvolution. It's like a multi-well deconvolution. You got like 3 or 4 laterals trying to back out the interference effects.
And I knew this was going to happen when they started drilling those stupid things. They drilled and completed them before they ever thought about the reservoir engineering. I was at the meeting where the guy said,
they had no answer for it.
We don't know what to do. And we're like, what the hell did you do this for? There's no way you can interpret it.
The next generation of Menara stations have gone into the well about 2 weeks ago. The first generation went in last year. The second generation has been in the ground for about a week now. And by mid-year, they're supposed to have a ton of data that they want me to have this model ready to interpret.
Well, and then, you know, when I was there 10 years ago, they were taking pressures every 5 seconds in all their wells, in all their new wells.
1 second.
Well, I mean, at that point, it was every 5 seconds. But they had a rate that was every month. But it wasn't really a rate. It was some guy back in Iran took all the volumes and allocated them back to the well because they didn't want anybody to know what they were really producing out of a well. If you wanted to know what a real rate was, you had to go and find the raw records, and they weren't going to give you that. The Saudis don't want their rates public knowledge.
They don't want the stuff leaving the country, but with these systems, we've actually got a Venturi meter on the Menard station
Yeah,
itself.
of course, and that's the live rate. So that's
You know, that's continuous rates on it. Plus, we have a water cut meter, which is a capacitance meter, which is good up to about 40%. I mean, it's ideal correlation up to about 40% water cut. Then you have reversal in the wetting and the continuous and discontinuous phase above 40%.
What Bobby and I are telling you, if you want the best toys, go to the Middle East. If you want the best problems, they're right here.
Yeah. Well, most of the solutions to the problems have to be worked out here. They sell the equipment over there, but then they come over here for the interpretation.
But toys, you know.
Yeah, they got the money to spend on the equipment.
Yeah, there's a few wells offshore that have that kind of jewelry in it, but generally speaking, they try to avoid it because of the subsea safety valves.
There are some installations like in India where they have distributed temperatures on thermocouples, not just DTS. They've got DTS in it as well, but they've got temperatures and some pressure, distributed pressures on sensors, on thermocouples, not just DTS. So they're starting to instrument the wells better, but it's extremely expensive, and most of them are just science projects at this point.
Let's have a quick quiz. How many wells are there in Saudi Arabia? Anybody want to take a guess?
300, 500,
Huh?
500.
It's more like, I think, 3,000 in that ballpark. It was less than 2,000 when I was there. How many in Argentina? 50,000?
Yeah, 45,000.
How many in the United States?
500,000.
I think the last count I saw was 850,000.
I saw it 750 the last I saw. And they're drilling.
See the difference?
They're drilling about 20,000 a year.
So for the railroad commission, don't they still use the 4-point test and 1-point test? Or using the pressure trend build-up analysis?
And he also put in the modern analysis.
Well, they still allow, for finite conductivity fractured wells, they still allow a 1-point test.
Oh, I see.
Where you have,
24 hours.
you run a 24-hour absolute open flow or flow rate measurement, and you draw a 45-degree line through it on the Rollins and Shale back pressure plot.
So where are my geologists? Here and here, right? In Texas, 2 points do not define a straight line.
Here, one
One
does.
defines a straight line.
Theoretically, on the Rollins and Shale plot, a 0.5 slope, or M value of 0.5, corresponds roughly to full turbulence.
Yeah.
That's what
One is
laminar flow. So they let you draw it through 1 point, 45-degree line, extrapolate to AOF.
Now, you guys are listening to all this, you go, these old fools, we'll just use a computer and everything else. But let me tell you, man, we've come all the way back to doing production diagnostics with simple plots because you simply cannot do anything else. If you want to spend your time trying to do really complicated analysis on shales, good luck. I'm happy to tell you the tools are there, but the expertise is not. What Bobby's showing you tonight is trying to lock in on some sort of a pivot point where you can say that's my defined system. That's good enough. You know, then going back and doing the higher order analysis is just a matter of the product. And as you mentioned, in Vanguard, the capless products and precaps products. You guys miss the good old days where you had to plot all this stuff by hand. That calculating everything essentially by hand.
All the pseudo pressure tables.
Yeah.
Yes.
That's all right. Every generation tells you stories like that. You'll be telling the guys one day. I mean, we had a workshop today where we talked about the future of unconventional analyses, and the kind of things that you're going to be looking at are going to be really complicated modeling. You know, what happened to us in our career, Bobby, with really complicated modeling? It just didn't. It doesn't. It's not justified.
In fact, one final comment. Like using Tom's technique of calculating the coupling point, to where all your late time stems collapse to a single exponential decline stem, like in this expression right here, gives you the anchor for these theoretical decline curve solutions. If you can generate, whether it's with Eclipse or whatever type of model you want to use, analytic solutions, numerical finite difference models, whatever, if you can generate the rate transient history of whatever kind of well configuration you got, whether it's multiple laterals in all different directions, curlicues, whatever you want, you can generate that rate transient history and convert it to decline curves. You can do this type of analysis. You just have to be able to generate that solution and be able to normalize it where you get an exponential decline in late time using these type of time functions.
You guys, I know you look at this stuff. I mean, this is a survey class. It's intended to give you background and everything. You look at that, and Bobby, we were grossly intimidated by this, right? Mm-hmm. And you derived all that.
You did a lot of this.
That's my point. I mean, I was where you are 30 years ago.
In fact, you introduced these two functions right here.
We needed something, like he said, we needed a tool to analyze rough data. So that was where the integral came from. Then we needed a derivative of that as a diagnostic. Yep. All this software stuff you see, it's all hidden. But we did this stuff because we had to. We had to have a methodology. People threw stones and tomatoes and everything else at us. We got up in meetings, and now we're thought of as geniuses. We're just guys trying to figure out a problem. I mean, it was an amazing time back then.
Well, like I say, if you can generate the corresponding rate transient solution and normalize it to an exponential function like that, you can do any kind of well analysis you want to with it. You can analyze the production performance of any kind of well, doesn't matter what it is, with this type of solution technique.
What he's telling you is the easy concept applies to the most complex case. Don't be fooled. We designed it that way, I'd say almost.
Mm-hmm. Any questions?
Mr. Wall, sorry.
What?
Huh?
What
We met at 6.
Oh, we did?
Yeah. Sorry.
I'm sorry.
That's all right.
Dr. Bennett used to go. But it'll be on the video. I'll mount it tomorrow. Mr. Wall's working on a parking case, right? You changed your mind? I thought you were going to work parking.
You told me that to
Did I? Did I really? What do you do?
Pardon?
You can still do mine. What was it you were going to try to do? Oh, you're going to try to catch it.
Well, I wanted to do some kind of, I wanted to get
Yeah, there's going to be a lot better data for mine.
The Bakken, they've actually got some decent data.
No, they
Yeah,
have
but-
great data for the Bakken.
In fact, they've got labs set up in Denver where they actually do the mercury injection. They got the cores. They do all kinds of tests on them.
Yeah.
Something like in the Eagleford. There's places in Eagleford there where you got API gravity of 22. Where do you think that oil is coming from? Austin chalk above it. Where you see the fractures in the Eagleford, look in the chalk above it. It's fractured all to hell. You get an API gravities of 22 out of the Eagleford. No way. All the water, salinity of the water, it's Austin water. And then you don't know what to count as height. A lot of the stuff that we're looking at there, you don't know what to, how much you're actually draining. Complicates the interpretation. But the Bakken's a lot cleaner. Plus, it's better permeability too. Because if you can take a core from the Eagleford in most places, put it in a centrifuge, you can't sling any liquids out of it. Those things make 400 and 500 barrels a day of liquid. Where's it coming from?
Yeah, I mean, you look at the Bakken and reverse calculate how much is coming out of the formation, and it's a thimble full a second.
Yeah.
I mean, like this guy at the end of your thumb,
It's amazing what you can get out of them.
This stuff's not producing oil, it's bleeding it. Bobby, thank you for, Bobby was here for our
You're more
workshop
welcome.
today, and I asked him if he would speak. I've got another speaker coming on the 7th, Dr. Rushing. He does have some issues with, he's a caregiver for his parent, so he may not be able to come, but his plan right now is to be here on the 7th and the lecture for 3 hours. I think I sent you the list of lectures. I did, sorry. You guys know. So Bobby, thank you for coming, and some of these guys will see you in Amsterdam. It won't be me.
You have one in Amsterdam?
I'll tell you what, man. If you win an award, I'll go to Amsterdam.
Well, I've got the paper. That's the only reason why I can go.
Thanks again for coming.
No problem.
Again, Mr. Wall will. Thanks. Now, you guys are going to see things from me coming pretty fast and furious now. I need your title and your thing. I'll be flexible on April 1st, and if you want to, you're not graduating, right?
No.
So, do whatever you want. I did give you an unofficial due date of July the 1st. I'll probably hold you to that. What I didn't tell you, and I'll put it in writing, is I grade these things line by line. I read every line very, very carefully. I want you to give me your best work. I'm figuring out if you're being naughty or nice. I listen to your video over and over again. I go back and read your paper again. I know you can't believe it all day with you there, but I do. So, do your best. Impress me. The only person you're competing against is yourself. Everybody, it's an individual sport. It can be on whatever topic you want. Just make sure. Santiago, you can learn how to format. Good. Everybody else? Oh, that's a great question. Yes, but, okay, I don't mind, but there have been a couple of people that have created a gargantuan document. You know gargantuan in English? That means unreasonably large. It's a great question. I will send a note and say, you know, if you need to go longer, that's fine. But do you know what it's like reading a 60-page paper? And I got to be careful because this is being recorded. But this young man had a premise that he was trying to prove. And he kept repeating it over and over and over and over again. And by the end, I was like, you're not going to win me with volume. You know, win me with something else. And I'm talking about 15 pages of text, not graphics. You can obviously, did I not make that clear? Sorry. You can have, I'm talking about 15 pages of words. So I'll clarify that. But if you want to go longer than that, it's your prerogative. But just please think about me, hovered over it, reading every line very carefully, you know, making sure you know what you're talking about. It's a great question. I will definitely clarify that. I thought I had. So, everybody else understand it? The 15 pages was words only, not and you can put whatever you want in the appendix. So, you know, if you want to put War and Peace in the appendix, that's fine. But Tom doesn't want to read 50 pages of you repeating yourself over and over again. And I'll tell you what is not good is if you decide that you're not going to use the format I've given you. I would really like it that you use the format I've given you. One gentleman decided that not only was he not going to use the format I gave you, he was going to increase the font size to like 15, and he did it double spaced. So he had something like 9 pages. So it was sort of like reading, you know, a book when you were in first grade. And I was like, where's the rest? There was none. So. But again, you're only competing against yourself. I'm not going to press you on, you know, if you decide you want to pursue the pocket, that's fine. But, you know, I'm not going to press you on your topic. I may ask you to clarify. And length isn't really that critical. I'm going to write a note on this as well. If you have any thoughts, send it to me. If there's something that's not clear. And I can absolutely assure you that everybody has an A. You know, you're the one that has to unearn your A. So, I've been extremely broad-minded and generous, because I want this to be something for you. I want you to create a relationship with me so that we're communicating, you're getting some feedback on what you're doing, if that's what you need, and I want to learn from you, as you're my tentacles, so to speak. I don't expect original work, but if you do something original, that's fantastic.
What the format say original?
An original view. Let me clarify that. I don't expect you to derive what he showed here and develop your own analysis technique. That's what I mean.
Oh, I thought the original,
It is going to be your work. Sorry. Yeah, we're differentiating here on the word original. I'm talking about you will write this paper.
Oh,
You will
I
not copy it. You'll not create it from other things. If you want to reference a graph, that's fine, but you're going to cite it. If you create a new interpretation of the data, that's original. That's fine. But do I expect you to go out, grab all the Uber data, grab all the pocket data, grab all the Niobrara data, make one of those funky triangle things you make, and tell me, here's where this oil came from, here's where that oil came from. If you can do something like that, fantastic. Do I expect it? Not really. The original aspect of this is where people come to me and say, I want to derive something. This is not that. It definitely will be original words.
yeah.
Sorry?
That's why only the portion is left with you.
I couldn't hear you.
So that's why only the portion is left with you.
Yeah. Well, I mean, still though, you will have to create your own interpretation, your own original interpretation. Are we okay? I mean, I hope you, since you're not an engineer, maybe it's not clear, but I don't expect these guys to create an original methodology on how to interpret a well test or something.
Oh, yeah.
Okay, sorry. I don't want anybody going out of the room thinking that they're confused about the definition of the words original.
Yeah, I have a question. If it's not original, you'll know after that abstract.
And I know I've reviewed some of your outlines for the most part. I'm very good. Most of the time you can hear me say add, and my reasons are that, you know, I want you to exhaust me. This is a very hard class to grade. This is probably the hardest thing. It's good for you. It's good training for your thesis. It develops the skills, that sort of thing. Okay, Bobby, questions, comments? Sorry, keep it.
Any questions?
You don't mind hitting start and restart on that, so we'll clear the memory on it.
Yeah, that's here. Just log
Okay,
off.
so, go ahead.
Log off.
Yeah, that's fine. I will try to see you again. The problem is that I have 7 service commitments between now and April the 5th. I'm talking about service commitments. Maybe tomorrow night, if I can get my act together, that'd be good, because I will be here tomorrow. That's the last day this week I'll be here. And probably let me try to do Monday and Friday night, so Monday the 31st and Friday the 4th, but I'll get back in touch with you. And I want you to come prepared to talk about your report if there's any questions about originality. I will try to do something tomorrow. That's a good idea, because I am here tomorrow night. Would you mind sending me a note about that link thing so it'll remind me? Thank you. Anybody else has anything, feel free to send it to me. And if you want me to share it with the group, just say, please include this in your discussion.
Which one you shut down with now, Tom?
Oh, they're done. Everything's fine.
Okay.
I'll shut it
I don't know if
down.
you need to shut it down any more than that or not.
Santiago, you okay? All Santiago cares about is he's getting on the plane August 31st, and he's never coming back to America, right? You hate it here, huh?
No, I like the US. I'm not much.
Of a Bush voter?
No.
Obama voter?
The study environment.
The 2D
The
environment?
studying.
Oh, you don't like
Study.
being a student?
No.
Why don't you guys explain it to him? How long have you been out of school? 15 years?
Yeah.
How long have you been out of school?
Oh, quite a bit.
Everybody get it? It's tough when you're old to learn things. Yes, sir.
But I'm fine.
Yeah.
As long as it's 1 year, I'm fine.
It's like prison?
No, not that much.
Choose your words carefully. All right.
How is the study environment in Argentina?
Huh?
How is the study environment in Argentina?
How's that?
Study environment.
You're saying, what's it like studying in
like?
Argentina?
No, it's the same, but I was 22 when I last studied.
Oh,
I'm
okay.
37 now, so it's 15 years I was studying.
You can move to the first.
Or the first.
Not the environment.
So we're not actually presenting this in the class.
You can, I will be here that week.
So like,
If you would like to do that, we could, but I still want your voiceover for my records.
So like what you personally want for grading is the presentation with the voiceover and the paper that's all.
Yeah, I would prefer a WMV than a voiceover, because voiceovers can be kind of wacky. And I was really a supporter of voiceovers until people started jumbling them up. One guy put a different voiceover on every page, and then another one kind of drifted off and screwed up a couple of slides. I'd just rather do one recording, and it's a lot easier to manage. But yeah, your paper will be in a PDF file, and your presentation will be underneath it in the PDF file. Same PDF. So I can probably give you an example, but I mean, it's brain dead simple. It's just- And that's it. So,
Sorry, I missed your presentation. I must have overlooked the 6 o'clock instead of regular 7. Sorry.
that's all right. You can have a couple of minutes. All right, guys, thank you very much for all your patience. And like I say, I'll do my best to be here tomorrow night. I'll double check. There's not anything scheduled tomorrow on Tuesday night, right?
Will you send an email?
I will definitely send an email. I need to double check my schedule. I need to do some other things, but I'm 99.9% sure that I'm clear for tomorrow night. Wednesday, I've got to drive to Galveston for a conference. All right, everybody have a good night.
Thank you so much.
I received last Friday a call from Petrobras to do an internship there now in May, and they asked me to give like 3 recommendation letters. The point is that like last semester I took reservoir engineering, but then I don't even know how it is now to ask him.
Just send me a note with their note. Is it in Portuguese or in
Yeah,
English?
no, it's in English. It would be probably in Houston. But the point is that they asked me like to give it on this Wednesday. It was like a really short time. Do you think you could do it?
Just send it to me tonight.
Thank you very much. Also,
They're going to email
try
or full letter?
to talk to Dr. Tinju because I took her course, but she's in China. I don't know if she's in China now, but she's traveling. So, okay. Thank you very much.
Make
It's
sure.
a letter of reference.
Yeah. Just send it to me.
Okay. Thank you.
Make sure you tell me who I need to send it to, like email address. Okay?
I think you sent me and I submit everything to you because they just sent me like a form.
So I send it to you.
Yeah.
Okay. That's
Okay.
all right. Just make sure you give me as much detail as possible. Forward all their emails to me.
Oh, okay.
And your current resume and anything else you can think of. So I just put it all in a folder so I can review it. Okay?
Okay.
All right.
Thank you very much. See you tomorrow.
Okay, great.
Thanks for the presentation.
Sure. All righty. You ready to go for dinner? Yeah. George is walking.
Stop and take a leak.
Yeah, yeah.
बोलो मैं मी 3 GB मतलब ओके मम्मी 3 GB का तो नो प्रॉब्लम 3 MB का तो एकदम कम है सर एकदम सस्ता नहीं मतलब सस्ता नहीं बोलूँगा बट आई वुड से ओके बोलूँगा कौन है क्या मैं अच्छा क्लियर से आता ना मैं नहीं नहीं हाँ लैपटॉप का अलग मम्मी वो लैपटॉप का अलग ना वो अलग मम्मी हाँ अभी 8 बजे मम्मी इधर क्या बोले मैं वो क्या मैं क्या मैं ओके 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 नहीं रेडी वैसे पर कुछ नहीं है क्लाइमेट अभी थोड़ा अच्छा है परसों मेरा गर्मी थी फिर भी अभी थोड़ा ये आ गया थोड़ा एकदम क्या भी अच्छा अच्छा वैसा अच्छा वैसा पूरा कैबिन में है। हम्म हम्म, हम्म। रिहा तस्लीम ऑनलाइन दिखाता है ना स्काइप में। मैं कॉल करता हूँ भैया। स्काइप में बोलता हूँ सर। वाइबर मांगा हूँ मैं। ओके वाइबर में करता हूँ। वाइबर आपको अभी इंटरनेट टैक्स एक्टिवेट हुआ क्या मालूम है, आपको देखना पड़ेगा। ओके एक सेकेंड।